раз мы остановились на обсуждении, что такое под... Okay, I should speak English. Last time we stopped at the discussion of what is a submanifold. So we had like two types of them, embedded and immersed. Submanifold. And there is a way how to, so submanifold by default usually is embedded for us. So it's a way how to say if your subset is embedded submanifold or not. Let me first formulate what is a subset satisfying case-wise condition. So let n be a subset in smooth manifold. So this is smooth manifold. And this is just subset. And we say that n satisfies k slice condition if for every p in n there is this smooth chart which contains p, so u phi, so for any p there is this u phi smooth chart of m, and this is chart around p such that, and such that if I take u, intersect n, and then consider image of phi with respect to that, then this can be described by subsets. So we have all elements x, 1, blah 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 x, I don't know, whatever is dimension of m, so m. So this is inside phi of u, right, which is inside Rm, such that so it's case-wise. So basically, first k coordinates they run as they wish, and the last m minus k coordinates they are just 0. So x k plus 1 equals xk plus 2 equals blah blah blah, xm equals to 0. So this is what it means for a subset of a smooth manifold to satisfy case-wise condition. And so theorem is that suppose that n is a k-dimensional embedded submanifold of M of M, then N satisfies case-wise condition. And then conversely, if a subset N inside M, smooth manifold M, satisfies case-wise condition, then on N there exists a smooth structure such that N is k-dimensional submanifold, well, embedded submanifold of M. Okay, so this is how you can. So you sometimes people use it by, as definition. If they want something more explicit, they just define it like this. And submanifold is when you can find some charts such that in these charts it looks like a intersection with k-dimensional subspace, Rk inside Rn. But
why is this a necessary condition for being a submanifold? Can it be the situation where just the charts are a little bit different, so in every chart this doesn't have zero coordinates starting from k plus 1?
Well, you always can find such, if you have submanifold, you always can find some such charts, right? And conversely, if you just have a subset, then you such that you can find such charts of M, then you can make it define like a smooth structure on N such that it is a submanifold.
In one direction, it is obvious for me that if we have such situation with this chart where we can nullify the remaining coordinates, then we have defined the structure. But otherwise,
yes. So
maybe we need
the other direction is also kind of straightforward once we know rank theorem.
Do we need some change of basis, maybe some or something?
Yeah, but it all will be hidden in the details, right? So let me give you a proof, but of course I will not. So all technical details can be you can recover it by yourself if you're pedantic enough. But let's not spend like unreasonable time for that in the lecture. So which direction? So suppose that N is submanifold. So suppose N is k-dimensional submanifold. Then we just apply the rank theorem to the inclusion map. N is included inside M. So this is so this you should check that this is map of constant rank, and this rank is k. But I mean, yeah. So but it takes, so it should include, right, tangent space, each tangent space of n at each point of p into tangent space of m, right? So it is of, should be of full rank at each point, so it's constant rank, which is a dimension of n, which is k. Then you just apply rank theorem, which is technical. That's where I hide all the details and say, okay, this is only about, you know, calculus on like multi-dimensional calculus, so let's not talk about this. And then, which says you what? If you have map of constant rank k, then you actually, then it actually looks as follows. It just takes for you. So I in some coordinates, it just looks like that. x1 blah 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 xk goes to x1 blah 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 xk and then zeros. So this is by the rank theorem. Okay, but then, well, there are some technicalities that you want to take your charts like small enough, like here, so that well, you have, that's where you use that topology is subset topology, because like you could, so chart here could be like something like that. So you have like a chart, and then you have like a n going through here, and maybe some, you know, piece of n also touches it. So you want like your chart on M small enough that it just takes this slice, and this can be made just because it's your topology is subset topology. Okay, but so again, details I just, you know, can't wait. And so this was what was not the obvious direction for you, right? So now another direction. So conversely, so suppose that I have n inside M satisfies k slice condition. Then, well, I just have these things that I just had on this board, right? So I have this, at each point of P, I have this smooth chart of M, right? So I just defined atlas using these charts, right? It's clear what I should do. So how to write this down? Right. So for each point, right, I have a chart of M. So let me now you know, index it with this point P and then 5. Right. So this is like a chart from the slice condition of M from the slice condition. Then I just define the smooth atlas on N. So just like that, it's just I take cover, which is UP intersect N, and phi P restrict to this intersection. right? If P intersect. So these pairs, as P runs over all the points in N, so this is smooth atlas. So the fact that it is smooth just comes from the fact that this is smooth chart, so all the transition functions, transition maps are smooth. We just need to check that, what do we need to check? That it is an immersion, right? But like inclusion is an immersion. But again, it's just immersion for obvious, like almost tautological reasons. You have coordinates in here, right? And which is just by construction is the first k coordinates in M at around the same point, right? And in your inclusion, so your di just sends d over dxi to the same kind of thing. This is for I from 1 to k. So it just, identity matrix. So it's just, simple as that. And so it's injective, so therefore it's an immersion. And then it's embedding by definition because, well, we just defined on N subset topology. So all this. So this is an open subset in subset topology, right? So nothing to check. Okay. All right. So then this is it. That's how you can check. So you can find such maps, but sometimes it's just in theory it's handy because like it's just more explicit way how you describe a submanifold. You just present these charts such that they look like that. So let me. Next important theorem that is used all the time is constant rank level set theorem. So constant theorem, constant rank level set theorem. And it says, suppose that, so these are all corollaries to the rank theorem, including this one. So it says that let F be a smooth map between two manifolds, so smooth map, and it's of constant rank. What else do I want to? Yes, I think that's everything that I wanted. So then, for any p from n, p inverse of, sorry, what am I writing? F inverse of p is a submanifold of M. And proof, well, again, I'm just hiding everything into rank theorem and previous theorem. You just so what should I say? So by the rank theorem, F inverse of P satisfies case-wise condition where K is rank of F. Yes. Moreover, I can also say submanifold of M of which codimension, right? Just to be more specific, of codimension M minus K, where, well, sorry, of codimension K. It's already right codimension, so codimension K, which is rank of F. So rank is codimension. Yes. So dimension is actually everything that is, squeezed into a point. So in kind of kernel, right, loosely speaking. Well, it's a dimension of the kernel of differential, which this is not loosely speaking. This is rigorous. Okay.
Please, may I ask you to clarify?
Yeah.
The right theorem states that we have coordinates so that the map F has zeros starting from some coordinate, and this gives us the condition for k-slice condition.
Yes. Well, basically, you can consider like in coordinates what is F inverse of a point. Right. So okay, let's recall. So F in some coordinates looks like this: x1 blah 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 xk. Right, and then, well, the rest, the rest of them, k plus 1, blah 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 x, I don't know whatever is dimension of M, and this equals, so 2x1 xk, and then zeros. Okay, and so
So F minus the pre-image of P is just all of the possible.
So it's we can choose it such that in these coordinates P is just phi of P is just 0. That's our choice, right? When we choose, at around any point, we can choose so-called centered coordinate system where this point is just the origin. So we chose so P is a point of n. So we chose coordinates in n such that this point P is just all zeros, right? And then I consider phi inverse. F inverse of P. So this will become zeros, and these are arbitrary.
Mm-hmm. Sure.
Well, that's kind of swapped. If I want to be like exactly like in case-like condition, right? I need to switch the order of coordinates, but that's irrelevant. So this choice gives us that F inverse of P is of this sort: 0, blah 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 0, and then x k plus 1, and so on. Okay, this is this thing. Also handy term, handy notion is what's called regular point and regular value. So let's define it. So again, let f from n to n be a smooth function. Then p from n is called regular point of m if dpf if dpf is surjective. And regular value, so some q from n, so it's is called regular value if any p from n such that f of p is q is regular point.
So submersion is regular everywhere.
Yes. And also points which this is some a technical moment, but actually like theorems usually proved taking this into consideration, that if point is not in the image, it's a regular value because there's nothing to check, right? So you check for empty subset. Right. So this is kind of a logical inclusion into this definition, but usually in terms that it is taken into consideration.
And also, if we have integral embedding, it is not regular everywhere.
In waiting,
not trivial embedding.
yes, that's true.
That's
yeah, well, that's kind of maybe counterintuitive because you want embedding to be as nice as possible, and so everything is regular. But I mean, terminology it is what it is. Yeah. Right. Corollary or whatever, another theorem. I don't know. Let it be something in between proposition. So let f again be a smooth map, and suppose that q. So this is inside the image. So it's a point which is regular in the usual sense. So q is regular value. Then f inverse of q is a submanifold of M. So this is very handy, I don't know, maybe for algebraic varieties. where your f is just, you know, bunch of polynomials, say from, you know, Rn to Rm, and you just need to check that differential of this, which is computed very easily, is surjective. And then you know that at this, well, at this particular point, and then you know that your corresponding algebraic variety is smooth. Okay. Anyways, let's see how this can be deduced from the case-wise condition, basically. So I would like to consider the subset of all regular points of f. So P such that P is regular point of f. So I claim that U is open. So idea is the following: I want U to be a submanifold, right? Then I can you know, restrict myself to this submanifold. Then my f becomes of constant rank, and then I can use you know, case-wise. Well, then I can just use the theorem, the previous theorem about level set of a map of constant rank, right? So, but how do I want to see that this is submanifold? Well, I just want to prove that it is open, and this is really easy. Just need to see that if P is a point in U, then, well, points close enough are also regular, right? But so this is clear because, okay, suppose P is in U, right? Then you consider dPf, right? And you consider you know, some matrix of this corresponding to some, you know, to some, so consider, so dPf, and then you have matrix some, I don't know, A, in some basis. Well, I need to pick basis in M and in D, in TP M and T F of P N. And the fact that it is regular means that some particular minor of this matrix is not zero. So actually, what?
No zero determinant.
Was that?
Non-zero determinant.
Yeah, I mean, yes, non-zero determinant, right. So P is regular, it's the same as we found a minor. Well, minor is already determinant in my books, but I don't know.
What determinant?
Determinant of submatrix, I thought that minor is a determinant of submatrix, but yeah, I don't know.
Yeah.
Maybe not. Well, maybe not. Yes, it's always ambiguity here. So let me think of minor as a determinant of a submatrix. Okay, then some minor of A is not zero. But okay, this is something. Not zero is an open condition, right? It's like it gives you an open subset, and it was called the risky topology, and which is weaker than just usual topology. So therefore, okay, aside of these words, if I, change it p a little bit, this minor still stays non-zero. Okay, because it's a continuous function. All right. So therefore, well, of course, I need to pick, consistent basis here. But let me. So this basis I can, pick as d over dxi's, right, with some chart around p. And so then this question is actually clear. So this minor stays non-zero for q close enough to p, and that's some hand-wavy proof of why u is open. Okay. All right. So now. Let me consider Q, which is regular value, which means that F inverse of Q is inside U. Actually, I need to write it, sorry, like that. Inside of U, so that's that. And moreover, I have F, if I can restrict it to U, right? And this is a map from U to whatever was the, to N. And this is a map of constant rank. So has constant rank. Has constant rank. And that's it. So I just apply the previous theorem to this situation. So I have map from one manifold to another of constant rank, and F inverse of Q is the same as F restricted to U inverse of Q, because of this condition. Right? The whole fiber lives inside U. Right? And so apply the previous theorem. And we are done. Okay.
So this condition is solves the issue with the requirement of the constant rank.
Yes. Yeah. So maybe it's hard to check whether your map has constant rank everywhere, but the message is that you don't need it. You actually need it to be you need. This also works for regular values, so preimage of regular values. Okay, then let me finish with this submanifold stuff and move on. Okay, so let me introduce further some operations with vector bundles on the smooth manifold. So, kind of new discussion. So operations with vector bundles. Well, the main goal is to introduce differential forms. Right. For that, I need to know what is which product of vector bundles, basically. So but let me start from something simpler. So I have, so suppose that I have two vector bundles, E1 and E2. Well, what can I do? I can consider, well, they are over X of the same vector space, and also I know the ranks of, so in just notation, rank of E1 is K1, rank of E2 is K2, right? And then what else do I want to fix? Well, I also will write G1, U1, U2, and G2, U1, U2 for clutching data for E1 and E2 respectively. So clutching data. For E1 and E2. And also, well, I can think of it as, well, to define on the same family of open subsets. Well, because if it's different, then we use our usual trick. We just make it, you know, smaller. This open subsets to make them smaller. Consider all the intersections, and then we can arrive at the same cover. Okay, so. Well, the message is that with vector bundles you can do the same things as with vector spaces, right? You just need to spell this out. Well, I can consider direct sum. So this is so now to define vector bundle. I need to do what? I need to define its rank, right? And then I need to define, like specify its rank, and then define clutching data, right? Which will be from GL sum. So this G's, which are functions, to GLK, where K is the rank, right? So here I just specify that the rank of this is K1 plus K2, right? And the corresponding clutching data, G, is just, well, on the same cover, is just G of U1, U21 plus G U1, U2. This kind of defines everything for me, right? Now, because I need something, some linear transformation for this, right? From this to this, which, and I think of this, right, as, which is, I guess, it's not like I think of that, it's just direct sum of RK1 and RK2. And so this is a linear transformation here. Anyways, also I can tensor product. Consider tensor product of E1 and E2. The corresponding rank is, of course, the multiplication, and then I think of RK1, K2 as RK1 tensor RK2, right? And then, of course, here I can consider G U1 U2, which is just, again, seems like rewriting the same operation over and over again, but it's just, how you define things. Right? This is well-defined transformation in here. Then, of course, I can consider, so number 3 and we discussed it already. Well, just take just one of them, say E1, and you can consider the dual. Dual, right? And the rank of dual is the same as the rank of the original one. We think of fibers as dual vector spaces to fibers of the original one, and the clutching data, we already discussed that when we talk about covector fields, is I don't know, we can just define it like G star. It is well, I take G corresponding to this one, and then take inverse, and then take transpose. Okay, then I can take symmetric tensor power. So symmetric, so it's number 4, right? So what I can consider, again, maybe let me, since I'm working with just one, so it's 4, and then since I'm just working with just one vector bundle, let me get rid of this E1 and just write E, and the corresponding, so let me just erase 1. Okay, so the corresponding rank is K, and then G is the clutching data. So what I want is to consider kth symmetric power of E, it's another example, and kth exterior power of E.
K should not be the same as the right.
Should not be same, yes. That's fair. What should it be? Let me. So maybe. D. Okay. What is this? Well, dimension is hard to compute. You can do it yourself. But I can just well, dimension. Well, what I would like to present is to present clutching data. For example, for this guy. So I don't know. Let me denote it like this. Would it be the maybe best, maybe not? I don't know. Again, not K. Just S D G. So this is like a clutching data for this guy. So I just need to specify from G. It works on. It is an element for fixed point in U1. Yes. For a fixed point on intersection of U1 and U2, this is from GL of S, D, R, K. Okay, like that. And so I just take tensor power D of GU1, U2, and it happens that this can be restricted. This just can be restricted to here. Because, well, because this formula is symmetric, right? So, in other words, action of GL. GL commutes with the action of permutations. That's like it was called Schur-Weyl duality, and so I can restrict it to any to any sub representation of.
The realization of symmetrical bundles of vectors as subspace,
Yeah.
vector space.
Yeah, we can do this.
Sometimes it's done by the.
Well, it's either way it works here, right? Okay. So I need to. So since I restrict, yes, I need of course to specify that. Okay. So what I think SD RK. What is this? So I think of this as something inside subspace inside RK taking tensor product with itself d times, and this is just this. These are all symmetrizations, so to say, of elements from here. What it means is just linear. So I need to write it like this: span over R of the following things: sum over sigma from ST V sigma of 1 tensor V sigma of 2 blah 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 V sigma of D S V1 blah 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 VD are inside RK. So inside RK. So I take, bunch of vectors, tensor multiply them, and then symmetrize, and consider all linear combinations of this stuff. Okay, this is symmetric tensors, of course. And then I take this stuff, and this subspace is invariant with respect to, so to say, action of GLK, right? And so I can restrict it to, SDRK. And that's my definition. And then, of course, I have this guy, which is just defined in a similar way, except here I have to put sign, right? So I just take lambda d RK. It's span over R of such things, sigma from SD V sigma of 1 blah 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 V sigma of D, and here it's the same. And then I also can restrict to lambda d RK. And so my lambda G, so clutching data for this guy, U1, U2 is just restriction of G tensor D, U1, U2, to this lambda D RK. Okay, what else can I do? So let me right away give the definition is that sections of T X tensor K tensor T star X tensor with some L, okay, are called tensors, so tensor fields, so called tensors on X of KL type. These are the things which physicists always like, and they write a lot of indices, like upper indices for all elements in here, as much as the K indices, right, and lower L indices here. So they call it, you know, something with a lot of upper and lower indices, they call it tensors. So what we call tensors this. Yes, and another definition, which is one of the main in the whole differential geometry, are K-forms. So K-forms, so sections of lambda K T star X are called K-forms, or I don't know, differential K-forms on X. Yes, okay. One more thing. So then I would like to go and study in more detail what I can do with forms. But before that, I want to consider example number 4, what I can do with two vector bundles. So I can also consider quotient.
That will be fifth example.
Fifth, yes. I cannot count, sorry. Fifth. So quotient bundle. So suppose that I have, again, E1 and E2, and E2 is in, as smooth manifolds, this is submanifold inside E1, and actually I have that I inclusion is one here. Vector bundle homomorphism. Well, injective, of course. Right. Now, in other words, to say that is that, well, if I have, so there exists clutching data G1, U1, U2 of E1 such that it leaves some subspace of dimension R2, well, which should be K2, invariant. So I'm considering this as a subspace inside RK1, say first K2 entries. Right, so if I have a sub-bundle, means that, well, I have a, I can obtain clutching data of the sub-bundle from the clutching data of the bundle.
This should be for each pair, one or two,
Yes,
and they must be consistent.
they must be consistent, yes.
See what is written here. G clutching data should be
So clutching data of E1 should be from GLK1, where K1 is in our example is greater or equal than K2. Then I'm saying that I can find some clutching data.
I mean, shouldn't it lie in the general linear group of this space?
This, yes, but this was written here as
It's
image.
the image.
Image, yes. So I'm saying just that some smaller subspace of the fiber of E1 is invariant with respect to the action of the clutching data. And then I just restrict it.
In this case, I is injective homomorphism between the bundles, which means, and injective means just that this is injective as a function.
Yes.
Is that implies that this would be embedding, or at least immersion?
It, yes, I think so. So you can go to trivializations, and then basically you consider. So it will be. So this is embedding,
Yes.
and so in trivializations it's just like how it looks like. Okay. So that's my setup. What I want is quotient bundle. All right. So therefore.
What is Russian for quotient bundle?
Фактор, вектор, ну,
Ну, понятно.
фактор освоения.
Ну, да.
Ну, как бы ничего
Ну, да, да, да.
неожиданного. Okay, so then I would like to consider. So I would like this inclusion, right? So say these are first K2 entries in the vectors in here, and then I just take P, which is, I don't know, consider natural projection from RK1 to the quotient. So since it's invariant, well, I can quotient, this will be like a representation of GL as well, right? So I take this and consider quotient. This is just a natural projection, and what I need is just this notation. So corresponding class is just V with brackets, and then I just consider the following clutching data for the quotient, G U1 U2, right? So this will be G for the quotient already. So it acts on a class. So again, this is so this G is from GL K1 minus K2. And I'm thinking of RK1 minus K2 as of this. And then it acts on that, just, I don't know, just bring it inside. So just take G1, U1, U2, acted on V. And since it moves RK2 to RK2, so then this is well defined.
Does this inclusion of bundles implies that we have the same base space X?
Yes, it does.
So the inclusion only on the level of vector spaces?
Yes, 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 that's a good question. Yes. So it's-
So this is just the restriction on the last coordinates.
Mhm. Well, you mean what is restriction?
Taking the quotient.
Well, it's kind of restriction, right? But you always can think of it as a, you always can add something from, it's a really quotient. You always can add something from this thing that you killed, and this will be the same.
Yeah.
Okay. So next, next thing that I want to discuss is how maps induce maps. So suppose that I have a smooth map from M to N. So how a smooth map induce a smooth map on the sections of Tm or T star or on K forms. So if I have this smooth map, I can talk about something which is called push forward of vector fields. Push forward of vector fields. So the corresponding notation is F with, I don't know, it's always a struggle, is it lower star or upper star? So I will follow my nose. I think I spent some time just trying to figure out which one is good one last year, so I will follow. So F with lower star will be a push forward. And one notation, I think I was saying sections on M I was denoting somehow like this, right? In the previous lecture. Yeah, but oh, sorry. Yes, maybe not like this, but I need like a vector bundle here, right? And I, for some reason, I would like to switch to gamma phi. This might be confused with symmetric power, so I don't want to use it. And this is like a common notation for sections on a vector bundle. Gamma phi. And so this guy is now from gamma of Tx to gamma of T, and we have M in N, that's right. So I have M here, N here, and then, so I'm thinking of section here as derivation, according to our discussion last time. And so this should give me a derivation in here. So how do I define it? So I just say that F star D, so it should eat some H, and this H is from C infinity of N. Right? And so I should be able to understand what this means. well, this is clear. What should I do? So D is something from C infinity of M, right? So I just compose H with F. So it brings me from M to N, and then from N to C. So this. Okay. Next thing is what I will want to do. So if I have F, what can I do with forms? So with forms, I can pull them back. So first, let's talk about one form. So pull back of one forms. And so I want to think of forms. So here I have some particular understanding of what a section of a tangent bundle. So I want some particular understanding with a section of cotangent bundle, at least locally. So for that, I would like to introduce, this, well, some basis for one forms on at least locally. So let me fix some smooth chart. Right. Then, well, and suppose that I have corresponding coordinates, x1, blah, 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 x. This is smooth chart where? On, well, let's see. Well, doesn't really matter. So it's just a little bit, it's discussion applicable to both sides, M and N. So let's say on M. Right. Well, let me consider x1, blah, 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 x n. So these are coordinates corresponding to this smooth chart. And then for each I, from 1 to n, I define the map dxi. So this is a map from U to where? To disjoint union of P over P in U of T, P, U star. Right. So I'm just, thinking of a section, right, as a map. As a map from, base to each fiber,
Okay.
right? And so I would like to define it like that. So I just fiber-wise I define dxip, right? So this is the value of dxi here. And it takes value in TP U star, and so it eats d over dx. So first of all, I should say that this is inside TP M TPU star, and second dxi p of d over dxj, so just dual basis, right? So delta ij. And here also I need at p. well, this is an element, this is derivation at the point P, so this is an element of TPU, and this, since by definition I know that this is inside, to define it completely, I need to define it on basis of TPU. So that's what I'm doing. And so it's
Just do basis.
just do basis, yes. Once I have that, I can say the following. So suppose, so let omega be a map, again, of the same kind from, well, but this time I would like it to be global. So from M to the joint union of TPNs star. As P runs over the whole. Such that, and I want it to be consistent with what I wrote, for any smooth chart, the restriction omega to U, well, chart U phi equals to some linear combination of dxi's. Well, actually linear over C infinity of U. So I should write sum of I from 1 to n fi dxi, where these guys are from C infinity of U. So suppose that I have such a map. So I'm just saying that these maps that look locally like this are the same as one forms. Okay. Then omega defines a section in our more abstract terms of Tm star, well, as follows. I just take P, right, and map it to the class of the following triple: P, U, and then F1 of P, blah, 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 if Fn of P. Well, of course, U should contain P, right? And this U should be a smooth chart. And then omega is written like that in smooth chart, and that's how I define section. Section should go from P to, to the total space of the vector bundle. Okay, I need to check that it is consistent, blah, 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 but it is because well, you need to check how dxi transform under the change of coordinates, right? And they transform in the same way. They transform using, well, they transform the same way as dual basis transforms. That's it, and that's how we define Tm star. So check is straightforward, or just follows from the from all the definitions that we have. Yes, and so conversely, of course, I can think of if I have a section. So I will finish in 1 minute. Then if I have a section, so any smooth section, well, given by star defines for me map omega such that locally it looks like that. So the other way works as well. So defines such omega. So once we now understand what are one forms a little bit more explicitly, so we can now define what is pullback of one forms. So this is, so we had f which goes from m to n. So then pullback, this one will be with upper star, will go from sections. So it's back, pullbacks. So therefore the arrow goes the other way. So from t star n to t gamma of t star m, and then it just defined like that. I have f star omega. So omega is an element in here, and then, well, so I'm thinking now of sections on t star m as such functions. And value of such function at the point p I will denote like this. So I just write p as a subscript. Okay? So now this guy should live inside t star of pm, like that. So this guy is inside here. And then it eats a vector, tangent vector to p from tpm. So let me put in some vector v. Now, this is by definition is just omega in the same notation, f of p dpf of p. So now this guy omega is from here, so therefore it is evaluated at the point f of p, right? F of p is a point in n, so therefore it is this guy is from t f of p n star, and it should eat vector tangent vector from tfpn. So this tangent vector from tpm, and by dpf it moves to the tangent vector to n at point f of p. And so then this guy knows how to eat this guy, and everything is consistent here. So this is the definition. And